37,000 liters of fresh water every single day, pulled straight from thin air in the middle of the Sahara. No electricity, no pumps, no pipeline bringing it in from somewhere else. Just fog, mesh, and gravity. To understand why that matters, you first have to understand how dry can actually get. There are places on Earth where it hasn't rained in 400 years. Not a drought, not a dry spell, 4 centuries with nothing. Weather stations in Chile's Atacama Desert have never recorded a single drop since records began. The Sahara itself, larger than the entire United States, gets less than 20 millimeters of rain a year. Some regions get none at all, year after year, decade after decade. And yet people have always lived there, in some of the harshest, most water-starved landscapes on the planet. So how do you build a reliable water supply in a place where water simply refuses to fall from the sky? Join Breakthrough Engineering as we uncover the answer. In 1499, Spanish conquistadors landed on El Hierro, an island off West Africa with no rivers, no lakes, and no visible water source anywhere on its surface. By every rule they knew, this should have been an island of the dying. Instead, they found a tribe with no thirst at all. The Bimbachi had hidden their source carefully, and it turned out to be almost absurdly simple: a single laurel tree. Its dense leaves caught the moisture carried inland by Atlantic trade winds, condensation formed drop by drop, and the water ran down the trunk into stone basins carved below, enough to supply an entire tribe, day after day. For more than a century, that one tree was the island's only water source, until a hurricane tore through it in 1610 and took the secret down with it. Centuries earlier, and half a world away, the Chiribaya of Peru had already worked out the exact same physics. Around 1001 AD, they built stone channels across mountain passes, angled precisely into ocean fog pushed inland by the wind, with sealed underground cisterns beneath to stop the collected water from evaporating in the sun. The principle is identical to the technology in use today. Same idea, same application, just different materials. Fast forward to the 20th century on a mountain called El Tofo in Chile. 100 fog nets, stretched across the ridge, collected 15,000 liters of water a day for the village of Chungungo below, a village that had previously survived on just 10,000 liters a week, trucked in from elsewhere and rationed drop by drop. For the first time in years, 300 residents planted vegetables right outside their own front doors, using water that used to be too precious to spare. It felt, for a while, like the problem was finally solved. Then, a storm rolled in with winds of 100 kilometers per hour. The flat nets, never designed for anything like this, caught the wind like fabric catches air. The steel frames bent, the cables snapped. Within minutes, the entire system was gone, and the only water left simply ran into dry sand. Investors around the world pulled funding from every similar project overnight, and the field was quietly declared dead. But the idea hadn't failed. The design had. A flat net in a storm doesn't collect fog. It becomes a wing. And wings generate lift, right up until something breaks. Engineer Peter Trautwein drew a very different conclusion from what had just happened on El Tofo. The net could never win a straight fight against the wind, so instead of fighting it, it had to stop existing as a target at all. He designed a 3-dimensional monofilament mesh, not a flat surface, but an open, flexible structure that hurricane-force winds pass straight through with almost no resistance, while microscopic fog droplets still cling to its fibers on the way past. The thickness of each individual thread turned out to be the detail the entire system lived or died on. Too thick, and droplets simply flow around it without ever attaching. Too thin, and they fly straight past before they even touch it. Only the right diameter holds them long enough to merge with neighboring droplets, grow heavy, and finally fall. Engineers took the new design to Bout Mesguida, one of the windiest peaks in Morocco, to test it against exactly the conditions that had destroyed the old approach. In winds of 120 kilometers per hour, worse than the storm that ended El Tofo, the structure didn't move. It didn't tear. It never became a sail. What they built next had no generator, no pump, and no connection to any power grid at all, because it needed none. A 10-kilometer pipeline had to be cut through solid rock by hand, using pickaxes and crowbars in 40-degree heat, with every single pipe carried up the mountain on human shoulders, one at a time, along a route as long as 100 football fields laid end to end. The force driving the entire finished system, though, has been understood since antiquity. A 500-meter drop in elevation generates 5 bar of water pressure through gravity alone, no machinery required. That's enough to reliably supply 16 Berber villages every day, without a single watt of outside electricity ever entering the equation. The change wasn't gradual. 30 days after the system went live, the time women in these villages spent fetching water dropped by 95%. A Saharan sandstorm doesn't tear these nets apart the way wind once did. It does something quieter, and in some ways worse. It coats them. Fine dust settles onto the damp mesh overnight, mixes with the moisture already clinging to the fibers, and dries by morning into a thin, stubborn layer of clay. The microscopic pores seal shut one by one, and within hours, a fully functioning water collection system quietly turns into a useless membrane that no fog can pass through. The fix, when it finally came from an unlikely source: the Atacama cactus, native to the very same desert where the very first fog nets had once been torn apart by wind. Under a microscope, its spines reveal a specific pattern of tiny grooves that stop dust from ever gaining a foothold. The first drops of morning fog simply wash each spine perfectly clean before anything can dry onto it. Engineers copied the same principle directly into the new nets. The first 15 minutes of morning fog are now deliberately used as a cleaning cycle, carrying the night's accumulated dust straight down into the ground below. Only after that brief window does clean, usable drinking water begin to flow. Today, systems built on this same principle run in Yemen, Oman, South Africa, Chile, India, Eritrea, Colombia, and Jordan, together covering 1,600 square meters of net and earning a UN Climate Award in 2016, all without ever burning a single kilowatt of energy. And yet, the engineers behind it aren't celebrating. Satellites are quietly tracking a shift in ocean currents, and morning fog in these key regions is losing 3% of its moisture every single year. As droplets get smaller, more and more of them simply fly straight through the mesh instead of sticking to it. The same physics that once made this technology work is now starting to work against it. A new, multi-layered structure is already in development, though it doesn't exist at full scale yet. A technology that took 1,000 years to build, from stone channels cut into Peruvian mountainsides, to a single tree on a Spanish island, to polymer mesh bolted onto a Moroccan mountaintop, is now racing against the very climate change it was built to fight. If you want to keep exploring the world's greatest feats of engineering, join Breakthrough Engineering for the next one.